So let me begin by thanking Arnab for this opportunity to co-organize this conference with Arnab, Tomaz, Roderich, and Anatoli. And I'm going to talk about many-body quantum chaos in mixtures of multiple species. This work has been done in collaboration with Bijay, who is sitting there. And Bijay is a PhD student at Ramanujan Research Institute. Our paper is available in on archive, this one. And also I would like to thank Professor Tomaz Prosen, because I learned about this field mostly through our collaborations, previous one and even ongoing one. Okay, so here is the outline of my presentation. I will briefly introduce many-body quantum chaos, which already our previous speaker introduced. Then I will talk about many-body quantum chaos for single species. And finally, I will come for the topic of this talk, many-body quantum chaos with mixtures of two species. Okay, so classical chaos is generally characterized by hypersensitivity of phase-phase trajectories to perturbation in initial conditions. Nevertheless, this phase-phase trajectory is not meaningful when quantum effects are significant due to Heisenberg uncertainty relation. And then we have to characterize quantum chaos by other quantity like the statistics of energy levels. So I will go through little bit details mostly for students. So let's consider we have a kicked top, and the Hamiltonian of this kicked top I can separate in two parts. One in H0, which is the base Hamiltonian, and H1, which is the kicking part, which is given by this delta function 1. So H0 represents precision around y-axis with precision frequency omega, and H0, and H1 is the impulse along the z direction with strength k, and small j is the total angular momentum for this rotor, kick top. So for this system, one can consider like for large j, we have a classical or semi-classical description, and for this particular system which is well studied, and I'm taking things from this reference. So for large j, we have this semi-classical or classical analog, which will show for small kicking classically regular motion, and large kicking it will show chaotic motion. Now we want to understand how it will look for relatively finite j for quantum system, or mostly like energy levels or quasi-energy level. So U is one cycle period or Fluke operator, from which we can calculate these eigenvalues, which I write as exponential of I phi m, where phi m is the eigenphases. So we can also define spacing for these eigenphases by phi m plus 1 minus phi m. So now in this plot, I am showing these eigenphases phi m with kicking strength k. So for small k, as I said, the classical motion of this system at large j would be regular, and one can see here the eigenphases mostly show clustering or level crossing. And for large k, we will have classically chaotic motion for large j, and this region we can see that a lot of levels are repelling each other, which you can see from here. So this kind of description leads to this level spacing distribution in the small k region showing exponential distribution, which we can relate with classically regular motion, and RMT description for the large k, which we can see from this level repulsion. So S tends to 0, that probability goes to 0. This leads to this well-known conjecture, BGS conjecture, which asserts the spectral statistics of quantum system whose classical counterparts exhibit chaotic behavior are described by random matrix theory. So it was mostly idea of Berry and Tabor in these two papers, which lead to this numerical test and conjecture. Now research over 20 years could explain such behavior for single particle systems whose corresponding classical dynamics are fully chaotic. Now, recently, a series of papers or a series of works could further establish such conjecture or relationship for non-integrable extended many-body systems where local degrees of freedom such as qubits or fermions have no classical limit. So these are the set of papers which again mostly started by these two groups of Professor Prosen and Chokar. And what these studies mostly teach us that if we calculate analytically spectral form factor, we will see after some finite time, which we will characterize as Thouless time, it matches with RMT prediction. For example, for circular orthogonal ensemble, the RMT prediction of this form, so leading order term is 2t, and then there will be correction. So second correction will be minus t square by minus 2t square by th, which we call Heisenberg time, which also introduced by previous speaker. Now, why we should study still all this analytical calculation of spectral form factor? Because it will teach more than what numerics will show. So it will teach us what is the mechanism, how non-universal behavior looks in these systems when we start with any particular Hamiltonian system or this kind of random unitary circuits, and also it will give the time scale over which one quantum system will acquire the universal RMT form. And I want to say our paper again with Professor Prosen, because these papers, few of them, first one was Hamiltonian system like kick transverse field Ising chain, many of them for unitary circuits. So many of them are, I will say, fine-tuned model, while this one we studied mostly for general model, and which our even present talk for mixtures also will be an extension of such theory, which is perturbative but seems to work for many Hamiltonian systems. So what I am mostly interested for single spaces, such model, like again I can separate by two parts. One, the base Hamiltonian, on the kicked Hamiltonian. Now base Hamiltonian, we can think, so this is a single space of fermion or bosons in 1D lattice, which have on-site energies are random, given by epsilon I, and we have long-range interaction given by this part, and it is periodically kicked by this H1 Hamiltonian, which has hopping or spreading as well as pairing. Now, why we choose epsilon I random and UIG long range? Because we want to make H naught super random, or energies of H naught super random, which will help us to calculate analytically spectral form factor. So now this model, if we take delta 0, has U1 symmetry, and if we break, or if we take delta non-zero, we'll have U1 symmetry broken. So that corresponds to total particle number conservation or violation. So spectral form factor was already introduced, but I still say a little bit. So we are going to calculate, as I proposed, statistics of energy levels or quasi-energy levels, and one can characterize that by mean and fluctuation of spectral density. So what we are mostly interested for this single cycle U operator or Fluke operator, its eigenphases, and we can define spectral density through these eigenphases, and the variance of this spectral density can be written by this R theta, whose Fourier transform to time gives spectral form factor, which we can write again by this U operator or Fluke operator as trace of ut into trace of U of minus t, and this averaging is what she was mostly talking about, self-average due to absence of self-averaging for such system, we average over the disorder which I have introduced here, epsilon I. So one can write U as two-step Fluke operator for V and W, where V is the kicking part propagator and W is the base Hamiltonian propagator. Now if I just do brute force numerics for that model which I have shown, we will see two behavior like this for spectral form factor with time. So when we have U1 symmetry or delta equal to 0, no pairing, then we see the systems had some non-universal behavior initially, then there is this ramp which is linear, and then their saturation after some time, which is Heisenberg time. And we are interested also in the non-universal region as well as the time scale above which this linear ramp appears. So this is for U1 conserved model, and if we do the same thing for U1 broken case, we see that non-universal region is very short, and we see linear ramp for long time. Now comes this analytical derivation. I will not, of course, present the analytical derivation, but I will try to say what exactly the result comes and what physical intuition we can get from such result. So let's consider we have this Fock state basis for this model for H0, which is represented by the occupation numbers at each site, N1 into NL. And since H0 is of this form, so N is an eigenstate of H0 as well as W, which is exponential of minus H0. Now, if we choose this basis, and I'm representing that in this figure where this dot, each dot represents on this Fock state basis, and different color I am representing for different total number of particles. So we can calculate the spectral form factor which we just introduced within one random phase assumption, which basically needs, as I said, super randomness for H0, which we can get by long range Hamiltonian, long range nature of the Hamiltonian H0. And what we get KT, so we get 2T, T is the time, into trace of MT. M is a matrix which can be written as this expectation of exponential of minus IH1 mod square, and V is just without mod square matrix. So we get 2T trace of MT minus T square function of M and V, and there will be higher order correction of T cube. So now in this one, if we do further, so now how to calculate them and how they are appearing. So they are appearing through graphs of like different type on this Fock state basis. So one can calculate different graphs on this basis and get what even this quantity will look. It will, in the leading second order correction, will look like minus 2T square by N, where N is the dimension of the Hilbert space.
I was just about to ask essentially if you could explain the intuition for the T squared and higher terms.
Yeah, I will show if I have time at the end. Okay. How's the second order term? So we call it second order. How's second order term? Okay. So now this one. So this one further, M is, as I said, is a bistochastic. Okay, I have not told. So M has this nature is a bistochastic matrix or Markov matrix. And since we know the Markov matrix has largest eigenvalue 1, I can separate it. So I am taking out largest eigenvalue, and rest of the trace I am writing by other eigenvalues which will be real as well as smaller than 1. So I write them by this one, and the second part or the second order correction is this one. So now if we want to see that how KT means KT from KT the RMT universal RMT form emerge, we have to see that when, because RMT behavior will say first order correction, first order form 2T, second order term this one, that means this term I have to neglect. So this will become smaller and smaller because lambda j's are smaller than 1 at longer and longer time. So our goal is to understand then the spectral properties of M, because if we know lambda j's, we know how KT will behave near this critical time, or what is the critical time, as well as lambda j's will give us non-universal region also. Now one can even interpret this M through return probability or survival probability, which also she introduced and many others also introduced. So PT, which I call return probability, can be written as expectation of M of T in this basis, Fock state basis N. So it says the return probability of any basis state N after time T time steps. And generally what we will see that PT N is order of 1 when T much smaller than this critical time which we call Thouless time, and PT N becomes order of 1 by Hilbert space dimension near or greater than Thouless time. Now, as I said, we need to calculate the spectral properties of M matrix or Markov matrix. For that, one can do numerical calculation of this M matrix eigenvalues, or rather we can try even analytically find them, which we can do if we can know that a simple, let's call Hamiltonian form of this M, which we tried to do in this paper, where what we means we have done it even in our previous paper, but in this paper we actually made it more formal way of deriving it. So we can do it at small parameter of j and delta by expanding these terms order in leading orders. We keep only until h1 square, and these dots represent here element-wise product or Hadamard product. With this, we can calculate even a Hamiltonian form for the fermion model, which I just introduced a few slides back, and this will become anisotropic Heisenberg model, where this coefficient or exchange coupling of this anisotropic spin-up Heisenberg model will given by these three quantities. You can see that two of these exchange are same, so it leads to an XXD type models. Now, since we have mapped the problem to a well-known Hamiltonian, we can calculate the spectral properties easily, and that will help us to calculate the time scale above which we have this universal RMT form for KT. Now, as I said that I am mostly interested the eigenvalues after 1. Now, these eigenvalues may or may not depends on the system size. If they depend on system size, or if they if they depend on system size, or if they don't depend on system size, we will see different behavior. But let's first consider the lambda j's falls rapidly as we increase j from the highest or second highest eigenvalues to smaller ones. So in that case, we can approximate only the KT with only keeping the first one. So we can write, and I am not writing the second order correction, 2t into 1 plus lambda 1 to the power t, which if we take that lambda 1 behaves as 1 by 1 minus t star, we can write as 2t 1 plus exponential of minus t by t star, and this t star is our Thouless time. Now, for isotopic Heisenberg model, for delta 0 case, this model becomes isotopic Heisenberg model because Cx, Cy, Cgi all become same. So for that case, so particle number conserved case, we have the mapped Hamiltonian SU2 symmetry, and we know it's a gabless spectrum. The second largest eigenvalue scale as 1 minus C1 by L square. So that leads to Thouless time scale as L square. And this behavior was observed before in these two papers. This is, I think, Professor Senkar group, and this is Chocker group. So these two papers also we found in this one. Now, if we take delta non-zero, which means particle number is non-conserved, so in that case, and we take delta non-zero as well as not same as j, we have all three eigenvalues survive, all three exchange coupling survives, and this leads to an XXG model with the G component, in this case actually X component, is larger than 1, that means the ratio of Cx by Cy larger than 1, that means it leads to a gap spectrum for anisotropic Heisenberg model, and our M matrix has U1 symmetry in this case. This leads to this Thouless time L independent. Now we can have even another case when j equal to delta. So in this case, Cy, Cj, both Cg, both are 0. So we have Ising symmetry in the model. And what we have now, we have a manifold of second largest eigenvalue which are degenerate, and that will lead to this T star scaling as log L, because we can write KT again like this form with all the degenerate eigenvalues, and that gives to log L. And this was seen in Tomaz' first paper in this direction, as well as from Chocker group calculation. Okay, so now just again coming back to that numerical plot, I showed for U1 conserved case, we had this kind of plot, U1 broken case, we have this plot. So we want to see from there, do we have Thouless time scale as L square? For that, what we did, we scale KT as well as T by L square, and we see that nice data collapse in this one. And also we see that non-universal region has collapsed in this one, and that actually also gives a scaling for that. And for the U1 broken case, we have Thouless time which is L independent. Now comes the final part of the talk, which is mixtures of two spaces. So motivation was that there are so many papers, many of them from Professor Prosen group also, with single spaces or single spaces in unitary circuits, but nature is full of multiple species, right? Our solids are made of electrons, phonon. Anytime we see here, these are made of photon and particles. So we should study mixtures. So that was the motivation where we started this model to think like we have listed mixtures of qubits and fermions and bosons. So again, I take this Hamiltonian, which is kicked Hamiltonian with two parts. One is H naught, the base Hamiltonian, which has random on-site energy for the fermions or bosons, and we have qubits whose on-site energy can, or which transition frequency can be also random, and we have long-range interaction for the fermions or boson. Then we kick that Hamiltonian by two kind of kicking Hamiltonian, one Giants coming type, where the mixing is such that it conserves total excitations. So what we are mostly looking for, competition between the mixing and spreading. So the spreading of fermions or bosons will compare with the mixing of fermions boson with qubits. And then we can have also another type of mixing, which is called Rabi mixing, which is this form, and that will break total conservation of particles. Means breaks conservation of total number of particles. So with this Hamiltonian, first I will discuss the result for Giants coming mixing. So this one for Giants coming mixing between fermions and qubits, and whatever I am going to tell, it also holds for Giants coming mixing between bosons and qubits, which are more physical. So what I am plotting here again, KT, the spectral form factor with time for weak JC mixing and for strong JC mixing. So what I mean by JC mixing here is the scale mixing G by J. So what we see for small G by J, we have nice data collapse for Thouless time when we look T scale by log L and KT scale by log L, which is shown here. And for strong JC mixing, when G by J greater than 1, that case we have nice data collapse when both T and KT scale by L to the power 1.85. This is, we get 1.85 because we have finite site systems, but I will show you analytically we get this is L square. So now I will try to understand this behavior, that why there is a crossing of Thouless time from small mixing to larger mixing in such two species model. So for that, what we do again, so for this model we go through all the calculation like this one. So we again have a Markov matrix for the full system. We mapped it to such Hamiltonian for this case also, and we get this MF of JC. So this is our mapped Hamiltonian, which has a nice closed form, which I am not showing here, but it has SU2 symmetry, and its eigenvalues exclude. Okay, so what SU2 symmetry helps, that it breaks different excitations, total excitation sector, but they are related. So, and that will help us to solve this problem analytically. So we look at n equal to 1 excitation sector and calculate easily for M matrix eigenvalues, and this is like this form for I not equal to 0 or the lambda 0 equal to 1. Now what we see here, that there is a competition between this hopping or spreading and G, the mixing. So if we take this part smaller than G by J, so we are taking somewhere that kind of scaled mixing is greater than this part. So in this case, what will happen, we can neglect this term, and then G square will come out and it will cancel this G square, and we will have 1 minus J square into 1 minus cos 2 pi I by L, and that will give us the lambda 1 again scale as 1 minus this L square kind of. So this leads to Thouless time order of L square. But so it actually also leads to a system size L greater than this critical LC, the critical length, above which we should see L square behavior for Thouless time. Though I am not showing such plots, I will explain that also. But if you take the other limit, when this part is larger than this one, G4 by J4. So then we can neglect that term, and this will exactly cancel this, and we will have L minus 1-fold degeneracy in the lambda I. So it will be order of 1 minus G square. Actually, there will be correction, which I'm just showing, but they are very negligibly small when G by J is small. So we have L minus 1-fold degeneracy in lambda I, which leads to this log L scaling. So for L less than LC, we'll see log L, and L greater than LC, we'll see L square. But one can also see that if we take L tends to infinity or thermodynamic limit, then G, J, none of them matter, and you will always see T star goes as L square. So finite system, we will see a crossover depending on this mixing strength. So for small mixing, we will see log L behavior for Thouless time, and for large mixing, we will see L square. But it has also physical consequences, right? Because if you have log L scaling, that means these systems will reach RMT behavior quickly, versus this one, which I have told for single species, we always have U1 symmetry. Sorry, in the U1 symmetry case, we always have L square scaling. Only for U1 broken case, we have log L. So I can see both of them, like log L and L square, U1 broken single species versus U1 conserved single species behavior within this total means total particle number conserved sector by this G by J changing. And in this plot, I am not showing such case, but rather what I am showing, because we can't actually go very large systems because this LC is relatively large and we can't go that. So I am showing instead of changing L, I am keeping L same but taking different G by J ratio. So this is like 1/4 and this is 4. Now I kind of summarize our main finding over all these works. So what I am going to say, that the effective Hamiltonian or the generating Hamiltonian for M matrix or Markov matrix, its symmetry is important because that determines the Thouless time scaling. And if we can find that analytically, of course, we can predict a lot of things. So here I am showing the first row, different Hamiltonian with U1 symmetry or U1 broken. U1 symmetry will lead is equivalent to JC mixing for multi-species, or R mixing for multi-species, U1 broken case. This column shows species, fermion qubit boson, fermion qubit mixing, boson qubit mixing. This first column shows T star or Thouless time scaling for particle number conserved case, and M matrix symmetry for the particle number conserved case. And this one again T star for particle number non-conserved case and the symmetry of M matrix. So what we see that for fermions and qubit, we have T star goes as L square due to SU2 symmetry of M matrix, and for the particle number conserved case, for broken case, we have two behavior, either L0 or log L, L to the power 0 or log L, depending on do you have U1 symmetry or Ising symmetry in the M matrix. And fermion and qubits behave similarly, but for boson, we see that for conserved case is L square due to SU11 symmetry in the M matrix, but this behavior, which we are not very sure that would it be like L to the power 0.7 or something else, but since the M matrix has E1 symmetry like this case. And this is the context even why I am constantly asking you S1 kind of thing, behavior. And for the mixing case, we have this crossover for log L to L square due to SU2 symmetry. Again for boson and qubit, log L to L square due to some emergent SU11 symmetry. And for U1 broken case, we have log L, because we have kind of this local U1 symmetry for all the qubits, and here also seems like log L for again this local U1 symmetry. So most of the things we can also find in this paper. Now I'll show you that how good this RPA results if you compare with exact result, exact numerical simulation like that. So here I am showing these things for Rabi mixing between fermions and qubits. So I'm plotting KT with T. We have this behavior. For direct numerics, we have this red plot, which is fluctuating, but not so fluctuating what Professor Kurchan was saying, going to 0. So I have also different interpretation for going to smaller value, and I'm comparing now RPA behavior, just keeping leading order and keeping the second terms, second subleading terms. Now you see that leading order, which is the black dash line, deviates little bit as you go longer time, but if we keep even subleading terms, we have very nice matching between this red line and blue lines. And of course, I have to keep lot of these eigenvalues, then only this nice matching will happen. So the summary is the study of spectral form factor, mostly analytically, would be very useful because you will learn about the mechanism, non-universal behavior, and time scale when a many-body system acquires a universal RMT form. And we have this new prediction, interesting I think, because at least for optical system with both photon and qubits, we can, I hope one should be able to experimentally check these things, including the field which I work a lot called waveguide QD. So there also I feel this kind of prediction can be tested. So our prediction is L dependence of Thouless time, process over from log L to L square with increasing giants coming, mixing between qubits and fermions or qubits and bosons in a finite side chain, and it will finally settle if you can increase system size long to L square. For Rabi mixing, both we think both for qubits and fermions or qubit and bosons, it should lead to T square proportional to log of L. Okay, so this is my end of the presentation, but now I'll come to this higher order terms. I have something for bosons which I skip. So for second order correction, these are again in that these graphs are plotted again on this Fox state basis presentation. So like this square you can think now presenting such graph. So we can have graphs. Okay, so maybe I have to say a little bit how we calculate the first order correction. So in the first order correction, we have graphs, or not correction, the leading order term, like this one, 2t into trace of mt. We have graphs where they like this one and another one following the same one. So that we call cyclic or anticyclic graphs, which gives this trace of ut into trace of u minus t. And that will give this 2t factor because we have t cyclic and t anticyclic graphs. Now for getting this one, we have to see if we can draw graphs beyond these cyclic and anticyclic permutations, and these are the crossing graphs, like single crossing graphs, double crossing graphs, and as you see, these are all also in discrete in time. So we were discussing and we found like these graphs as little different from what people have done for semi-classical periodic orbit theory, where the graphs are mostly in continuous in time. And also we have repetition of basis vectors, which we have to exclude from our contribution. The repetition can come with also crossing. So all these terms, if we add up, then we will get this term.
Okay, so just continuing along those lines. In the linear term, we have this trace m power t, which is usually interpreted as a return probability.
Yes, I also
So what about f of mv? I'd assume that that would also be a return probability.
yeah, that
but you have
also
something
return
different.
probability, but as I am trying to interpret, there are different type of graphs. And I think Thomas might be able to comment more. He related those graphs, these graphs with something in semi-classical periodic orbit theory, Sieber-Richter mechanism.
Yeah.
So,
So I guess.
but in that mechanism, you do not have these graphs. Okay, so you have only these two kind of things.
Okay. So I guess that will just produce this like constant coefficient expression in terms of t squared.
Yeah, because what we find, all that subleading eigenvalues terms cancel out, which you can see for this graph, we have this subleading contribution, this one, which exactly same as this one for this graph.
Okay, but so I was just wondering if you had some intuition for what that f of mv could be thought of as.
Physically?
Yeah.
Right now, maybe I can't say directly, but I can tell you later.
Looks like we've seamlessly went on to the interaction section of the talk. So let us first thank Dibyendu for a very nice talk. And if there are more questions.
In the case where you have Z2 symmetry,
Which case?
I thought in one of the cases you have this Rabi model, right?
Yeah.
That has a Z2 symmetry.
Actually, this anisotropic Heisenberg model, even for single species, which we map this one, also has for U1 broken case Z2 symmetry.
Z2.
So
So whenever you
Rabi
have
model is also U1 broken.
so is the statement that whenever you have a Z2 symmetry, you have this log L, or because in your
I
table,
think that G2 is log L comes from Ising symmetry for at least single species, because our model becomes just Ising model here. So Ising model also has Z2 symmetry as well as some, because it's not that huge degeneracy due to G2. That's right, because G2 can't give so many degenerate states.
okay. Yeah, I guess also it was related that if suppose you have, let's say, decay lattice,
Sorry,
a decay model
decay model
on a lattice, for example, then would you expect the same kind of thing as just by looking at the symmetry? Can you just say
no, because without knowing the M matrix, we don't know the symmetry. From the actually, okay, I have things to say that. Let me come to that point. So you see that U1 symmetry is the Hamiltonian symmetry, but then we can get, depending on different species or model, the emergent symmetry is different. Right, I can get SU2, SU11. Here we can get Ising, maybe one which is also related to Ising. So it's difficult to say what will be the emergent symmetry for the mapped Hamiltonian, and that will help to say about the scaling.
thanks.
Okay, maybe it's a naive question. So in many of the talks, we saw that this Thouless time scales exponentially with systems.
Yeah, even she was
Yeah,
saying, and
but
I have even problem with that because I think the U1 because her model is U1 conserved, it should be L square, but she is claiming exponential in
but
L.
in most of the talks, what it looked like it's
No, but even Lev talks for XXG model, he has that scaling L square exponential of W by omega, which omega some numerical parameter W is disorder strength, so that has L square. Maybe I because I am not sure, and I can say that this L square is not what even in my paper with Tomaz we have told. This has been shown in these two papers also. So this 2019 is this paper. Friedman, Chan, Luca, and Chokar, they also have L square for random unitary circuits. And the other paper with field theory, they also have L square.
Maybe we have time for just one more question.
So there's not a question, like more of a comment potentially on what might be going on with the Thouless times. So in Dea Santos's talk, the spectrum was cut off with some edges, if I understand correctly. And that cutting off leads to this power law decay in the Fourier transform. But here, I guess there's a Floquet system, there's no cutoff, it's like a smooth circle. So what you're really capturing is you don't see the effects of that cutoff and you're just capturing the inherent Thouless time. I think that is the difference.
Yeah, I could not hear the last part what you said.
So in this Floquet case, there are no cutoffs, right? Or even if you're taking the full spectrum without cutting it off, you won't see the contribution.
Okay, so you're saying she is cutting some
so
parts.
that cutoff leads to that power law
might
decay.
lead to.
And here, if you don't cut anything off, you will see a more like intrinsic Thouless time that may be like polynomial.
Yeah, that
or
might
log.
be a point. I guess we can.
It's not that I am cutting. The system is finite, so the density of state is finite. That's it. So it's the one-point correlation. It's an isolated system. It's not driven.
Yeah, we are at infinite temperature, right? Because we are Floquet system. Because even you are saying you also have that kind of exponential, right, for your SOIK kind.
Okay, let's thank Dibyendu again for the talk.